You're looking at the gates of the Middle East Technical University. Past this entrance lies one of the most rigorous academic hurdles in the engineering curriculum, the Math 120 first midterm. The syllabus for this exam covers a specific gauntlet: infinite series convergence, power series, Maclaurin and Taylor series, and three-dimensional geometry. But mastering the formulas is not enough to pass. This exam is engineered with relentless time pressure. It is designed to punish inefficient problem-solving. Professors accomplish this through the examiner's trap. They write questions that appear to be standard calculus problems, inviting you to differentiate or calculate a limit, but are actually structural tests of your algebraic knowledge. Take this prompt from the summer 2018 paper. It asks for the 120th derivative of the function f of x equals x cubed cosine of x squared over 2, evaluated at -1/2. Or consider a seemingly simple recursive sequence. The exam will ask you to prove convergence and find the limit. While guessing the limit takes seconds, writing that answer down without a formal proof results in 0 credit. Success in Math 120 depends on shifting from brute force calculus to the application of theoretical definitions as precise calculational tools. Let's examine that summer 2018 question. The paper asks for two things: the limit as x approaches 0 of f of x minus x cubed over x to the 7th, and the 120th derivative of f of x. Attempting to solve the limit with L'Hopital's rule, or find the derivative using the product and chain rules, is a fatal error. You will simply run out of time. The Taylor coefficient Cn equals the nth derivative evaluated at a divided by n factorial. We bypass differentiation by substituting x squared over 2 into the standard Maclaurin series for cosine of x, mapping new exponents, distributing the x cubed multiplier, and updates every degree to construct the final series. To solve the limit, we evaluate the leading terms. Subtracting x cubed cancels the first term, leaving a clean polynomial division that immediately yields -1/8. For the 120th derivative, we isolate the coefficient attached to the term where the exponent equals 120. Here, students often fail. The question asks for the derivative. You must isolate it by multiplying that C120 coefficient by 120 factorial. While textbooks often introduce Maclaurin series for approximation, METU examiners use them as exact algebraic tools for bypassing differentiation that would be impossible to complete under exam conditions. Question 6 from the same paper presents a different trap. You are given a complex power series and must determine its interval of convergence. Most students correctly use the ratio test to establish the open interval and the radius of convergence. However, the ratio test is inconclusive at the boundaries, where the rubric allocates most credit. For the x equals 1 boundary, evaluate the series by plugging it back into the original summation to create a new static series. You evaluate this new series using the limit comparison test. By comparing it against the divergent harmonic p-series, 1 over n, you prove the endpoint diverges. At the second endpoint, plugging in -2 transforms the expression into an alternating series. The grading here is strict. To use the alternating series test, you must explicitly write down the proof that the sequence of terms is decreasing and that the limit approaches 0. Finding the radius is the prerequisite. The true test of a student's preparation is the rigorous execution of convergence tests at those boundary limits. The demand for rigor is most evident in recursive sequences. Question 1 defines an plus 1 as an over an plus 1, with a1 equal to 1. The trap is the intuitive algebraic shortcut. If you set the limit L equal to L over L plus 1 to find 0, your work will be crossed out. You must establish convergence using the monotonic sequence theorem first. Step 1. Establish a bound by proving via induction the sequence is bounded below by 0. Step 2. Prove it is monotonically decreasing by algebraically showing the denominator exceeds 1, meaning terms strictly shrink. The grading rubric requires an explicit citation of the monotonic sequence theorem before the final limit calculation is considered mathematically valid. This theoretical standard applies across the paper. When testing for absolute or conditional convergence on a series with sine or cosine, the root test is inapplicable because the limit of the roots for those oscillating functions does not exist. The correct numerical result is worthless without the textbook standard proof required to validate it. Use the survival protocol for pattern recognition. If a limit is too complex for L'Hopital's rule, or if an integral lacks an elementary antiderivative, switch to series algebra. Before entering the exam, you must memorize 4 mandatory Maclaurin series: e to the x, sine of x, cosine of x, and 1 over 1 minus x. Expect a question on estimating error bounds. This requires Taylor's formula with the Lagrange remainder. The 3D geometry portion of the exam is your opportunity to collect points efficiently. It typically tests standard applications rather than theoretical traps. Focus your geometry review on 2 high-yield calculations: the intersection of a line and a plane, and the distance from a point to a plane. To recap the essential protocols, for recursive sequences, prove the sequence is bounded and strictly monotonic before solving for the limit. For power series, explicitly test the endpoints using limit comparison and alternating series tests. And for higher-order derivatives, construct the series, isolate the single coefficient, and multiply by n factorial. The METU Midterm 1 is a predictable structural system. By applying these theoretical definitions to bypass brute force traps, the exam becomes a manageable structural exercise.